Thank you, and I would like to actually thank you for the opportunity for me to present Nobleo technology. We're a service provider, we're an engineering company in the Eindhoven area, we're a service provider. We're part of that ecosystem, which has been talked about a lot, and we believe in the ecosystem also. And in that sense, I will be coming back on that a little bit later maybe, about how we connect, let's say, not only engineering, but also the manufacturing. But let me start with share a little bit of our DNA. So these are, let's say, we're not a big company, we're a company with small in size, but with happy engineers, because we also believe that happy engineers can do magic. So we pay a lot of attention to, let's say, create an atmosphere where there's interaction, where there's openness, there's, let's say, drive and happiness. Also, let's say, our location. So this is the Netherlands and Brabant. This is the Eindhoven area. I always like to say that over here is ASML. That's the people with a lot of money. And up here is the university. That's the people with a lot of brains. And we're just in between there, right there. So. And we are located in a church, which is, I call the Holy Church of Mechatronics. We basically have three divisions. I'm not going to dwell on all three of them, only mainly on the mechatronics, but I want to say something quickly about our autonomous division. So we are working in autonomous systems, and it's been mentioned also precision farming or autonomous farming is something that's hot and happening in the Netherlands, and we're contributing to that. We have, let's say, localization systems and algorithms that we provide to people who make tractors, and they can automate those tractors. And I can talk for ages about that. We have a group which is focusing on embedded and electronics, of course, for mechatronic systems, which is the combination of mechanics and actuation and electronics and software. That's an important part, but they also look into, let's say, other activities. One of them is typically when we look at problems with the battery management systems, thermal runaway. I had a few videos in here of exploding batteries, but I only got 10 minutes, so I decided to skip those. And then mechatronic systems, which is, let's say, the main topic that I would like to talk about. We use, basically, the way we work is we use the V-model paradigm, which has been talked about previously, which is very common in our area, which is a systematic way of taking a, let's say, problem, some kind of a set of requirements, and decomposing that into modules and decomposing that into smaller parts. At the end of the day, you have a bag of parts, so to say, at the bottom of the V. And then once you have those parts, you start to put them together, and then you cross-check when you have put a module together or a group of modules, a subsystem, and a larger system. You check that against your original requirements. That paradigm, that way of developing is very common for engineering companies. What we do in addition is we connect with Nobleo Manufacturing, which is a sister company of ours, who is more into industrialization, not so much into the development modules, but industrialization. And we try to, let's say, link in that early supplier involvement. I was saying a moment ago, we believe in the ecosystem, because that ecosystem means that if you want to accelerate development, you have to team up. You have to get together with the people ahead of you, the people behind you, and as an engineering company, the people behind us are the people who have to make it and build it. So we team up, and we have this early supplier involvement. We call that Design House Plus as a proposition. And that's one of the things that sets us apart, and we have proven already that we can accelerate development, especially once you have defined your system, when you want to build it, set up the supply chain for your OEM or for your customer. That helps, and that works. And we also believe in that way of doing things. If we look at what we are, let's say, best known for, over here, we're, let's say, specialized in mechatronics. Again, the science of controlled motion. A lot of these equipment, and again, the equipment is becoming more and more complex. The shrink basically has continuously forced us to make more precise motion. At the same time, more fast motion, because the precision you need for your processes, for your lithographic processes, for your 3D integration, the speed you need to make it an economic, interesting tool. So there's always a challenge there for the design engineers to make it preciser and faster. So we have a lot of knowledge in the area of these mechatronics, motion systems, actuation systems, control, feedback systems, embedded software, smart software that does self-diagnosis of systems, that can auto-calibrate these systems. There is precision engineering, which if you go back later to our table, I can show you a little demonstrator of, let's say, flexible mechanisms and flexible hinges, typically a part of precision engineering. System dynamics. Usually the biggest threat for accuracy is some kind of a motion from the outside world. So system dynamics that come in and basically are trying to keep you off track, and how to manage that, keeping them out, controlling them away. And also, let's say, feedback control design. Here we are. Feedback control design. So at the end of the day, if you can't manage the disturbances, you have to use feedback to reduce the effect of disturbances. So we package all of that into, you could call a system engineering way of working, and that's how we basically tackle these challenges from a complex set of requirements down to a functioning, reliable, makeable, orderable, manufacturable piece of equipment or module for an OEM. These are, it's a little bit of a repetition. This is how we do it, this is what we do, and this is how we do it. We have a systematic way. We do also a little bit of test tooling, all of that. I don't want to elaborate on that too much. Here we have, let's say, a diagram in which I'm trying to show, let's say, these different parts that are part of a mechatronic system, which you all have to basically have in your scope and you have to manage somehow. There's embedded software, there's mechanical systems, electronic systems, and these are some of our expertises that we're known for and that we provide to our customers. I want to go through and give you just, because the best thing is, of course, to have a look at a couple of examples. This is part also of what we believe in, which is a kind of a V cycle you see over here. So we do a lot, of course, like these modern companies in the digital world with digital twins, but we also go to the Gemba, say to go to the real life world quickly. We make a habit of having quick iterations. We have a good set of suppliers around us that can basically take an iteration that we've done here. So in this case, we were designing something for a certain performance, and then we build the prototype quickly and measure it. So it's not only designing, it's also verifying, measuring it, and closing the loop, basically, is what you had in mind in your PC. Is that really what happens in the real world? And usually the answer is no. And so we build it, we measure it, and we learn. And this learning cycle, which is becoming more and more complicated because, let's say, the accuracies are getting tighter and tighter, is something that we're continuously trying to accelerate. We're using AI to make things a little bit more efficient. You have to keep up in this race to be able to perform at a level that is required for the innovation in mechatronics and semicon, and coming up also now in photonics. This, again, is something about how we take the industrialization and the design development and we put them in parallel, early supplier involvement. So as soon as we start to think we know this is what it looks like, we call in the suppliers and get them around the table. We have a clean room to do, it's not very impressive, it's a small clean room to do prototyping. And then here's one or two small examples that that I'd like to share with you. This up here is, let's say, a way of doing the brainstorm in the beginning, going from morphological ways. You have some kind of a requirement. You want to move from A to B with a certain accuracy, and there's lots of ways to do it. So we generate ideas, and we talk to our customers. We say, this and this and this is the option. We would go for option B. What would you like? The customer always decides. And then, as time goes by, it trickles down into a design. Here I have a system in which we've used a lot of this technology, of course, is using Lawrence type of actuators, the kind of stuff that's used in the semicon industry, air bearings and things like that for cleanliness. I can talk long about that. If you come and see me, because I'm going to stop now, if you come and see us, At the table over there, you will recognize this beautiful purple color. There's a tablecloth over there, and I will be there, and I'll be glad to talk to you about all of this stuff and show you some of the other cool demonstrations that we have there. Thank you.